Namaste, my friend, and welcome back to NEET Chemistry with Typical Monk. This is Class 3, and today we go deeper inside the atom. Last time, we watched bar-drawn neat little orbits, like planets around the sun. But nature is subtler than that. An electron has no fixed path at all. It has only a home address, written in 4 numbers, and a hazy cloud of space where it is most likely to be found. When Sarah first heard this, she asked, if we cannot say where the electron is, how can we ever describe it? And that is the perfect question. We describe it not by a point, but by an address and a shape. Today, one idea at a time, we learn to read that address, draw that shape, and fill every atom with confidence. Take a slow breath. Let us begin. So what will you carry home from today's class? First, the 4 quantum numbers N, L, M, and C, the full address that names exactly where an electron lives. Second, the shapes of the s, p, and d orbitals, and how to count the nodes hidden inside each one. Third, the 3 great filling rules, Aufbau, Pauli, and Hund, the laws that decide the order electrons go in. Fourth, electronic configuration, and the famous chromium and copper anomaly, where the atom breaks the simple pattern for the sake of stability. And fifth, the NEET drills. Assertion and reason, match the column, and how many are correct, so that everything you learn today, you can also score with. Ready? One idea at a time. Every electron in every atom has a unique address, and that address has 4 parts. The first is N, the principal quantum number. It names the shell, and it sets the size and the main energy level. N can be 1, 2, 3, and so on. Bigger N means a bigger, higher energy orbital farther from the nucleus. Think of it as the floor of the building. The second is L, the azimuthal quantum number. It names the subshell, and it decides the shape. L runs from 0 up to n-1, and we give its values letters. L equal to 0 is S, 1 is P, 2 is D, 3 is F. So L is the shape of the room. The third is M, the magnetic quantum number. It names the orientation, which way the orbital points in space. For a given Lm, takes 2L plus 1 values, running from -L through 0 to plus L. So a p subshell with L equal to 1 has 3 orientations, 3 p orbitals. And the fourth is the spin quantum number. Each electron spins one of 2 ways, plus 1/2 or -1/2, spin up or spin down. 4 numbers, 1 electron, 1 unique address. No 2 electrons in an atom can ever share all 4. Now let us actually see these homes. Look carefully at the shapes on screen. The s orbital is a simple sphere, one smooth ball of probability around the nucleus, the same in every direction. When L is 0, there is no preferred direction at all. The p orbital is a dumbbell, 2 lobes stretched along an axis, with the nucleus sitting in the pinch between them. Because L is 1, there are 3 of these dumbbells, pointing along the x, the y, and the z directions. The d orbital is more elaborate still, 4 lobes, a cloverleaf shape, with L equal to 2 and 5 different orientations in space. As L grows, the shapes grow richer. And here is the idea that ties them together. The node. A node is a place where the electron simply is not found. The total number of nodes in any orbital is n-1. Of those, the angular nodes equal L, and the radial nodes equal n-L-1. Hold that formula close. NEET asks it again and again. Let us slow right down on nodes, because this is where easy marks are won and lost. First, what is a node? A node is a region of space where the probability of finding the electron drops to exactly 0. The electron is on either side of it, but never in it. Second, the angular nodes. These are flat planes that pass through the nucleus, and their number equals L. So an s orbital with L equal to 0 has no angular nodes, while a p orbital with L equal to 1 has 1. Third, the radial nodes. These are spherical shells of 0 probability nested inside the orbital, and their number equals n-L-1. And now the beautiful part. Add the angular and the radial together. Al plus n minus L minus 1 and the L cancels clean away. What remains is simply n minus 1. So the total number of nodes in any orbital is always n minus 1, no matter its shape. Time to solve a full NEET favorite together. Slowly, the monk's way. Write the ground state electronic configuration of chromium, whose atomic number is 24, and then count its unpaired electrons. Step 1. Start from what is given. Chromium has 24 electrons, and we place them one by one in order of rising energy, following the Aufbau path. Step 2. The naive fill. If we followed the simple pattern blindly, we would end with 3d4, 4s 2. But this is not what nature chooses for the ground state. Watch closely. Step 3. The anomaly. One of the 2/4 electrons slips down into the 3d subshell, giving 3d5, force 1. Now the d subshell is exactly half filled. Step 4. Why does this happen? A half-filled 3d5 is unusually stable because of something called exchange energy, the extra stability an atom gains when parallel electrons can swap places among equal energy orbitals. Nature pays a small price to reach that half-filled comfort. Step 5. Count the unpaired electrons. 5 electrons sit singly in the 5d orbitals, and 1 sits alone in 4s. That is 6 unpaired electrons in all. Notice the path: given, naive fill, anomaly, reason, count. The very same logic explains copper, which becomes 3d10, force 1 for a full d subshell. Now, the master map, the order in which orbitals actually fill. Look at this staircase of arrows. First, the Aufbau principle itself. The word means building up. Electrons always occupy the lowest energy orbital available before moving to a higher one, filling the atom from the ground floor upward. Second, how do we know which orbital is lower? By the n plus L rule. For each orbital, add n and L together, and the orbital with the smaller sum fills first. 4 Sn plus L is 4 plus 0, that is 4. For 3d, it is 3 plus 2, that is 5. 4 is smaller, so 4 is wins. Third, when two orbitals tie on n plus L, the one with the lower n fills first. This is exactly why 4s, though it comes later in name, fills before 3d. Fourth, the practical trick. Just follow the diagonal arrows down the staircase, one after another, and you will never light the order wrong. Lisa used to memorize the sequence by force and kept slipping. The day she started drawing the arrows, the order became automatic. Now sit up straight. These 5 lines are what NEET actually asks year after year. 1. The total number of nodes in an orbital is n minus 1. The angular nodes equal L, and the radial nodes equal n minus L minus 1. This trio is tested constantly. 2. Each subshell holds 2 L plus 1 orbitals, and that is also the number of magnetic quantum values. So S has 1, P has 3, D has 5, has 7. 3. The Pauli exclusion principle. No 2 electrons in an atom can share all 4 quantum numbers. This is why an orbital holds at most 2 electrons, and they must have opposite spins. 4. Hund's rule. Within a subshell, electrons occupy separate orbitals singly, with parallel spins, before any pairing begins, and half-filled and fully filled subshells carry extra stability. 5. Remember the 2 anomalies called. Chromium is 3d5, force 1, and copper is 3d10, force 1. These 2 are asked almost every year. Let us drill the NEET way. Remember the 4 options. Option A, both statements true and the reason explains the assertion. Option B, both true but the reason does not explain. Option C, assertion true, reason false. Option D, assertion false, reason true. First one, the assertion. Chromium is 3d5, force 1, not 3d4, force 2. The reason, a half-filled d subshell has extra stability. Think like Sarah. Check each statement alone, then check the link. Is the assertion true? Yes. Is the reason true? Yes. But is stick, combi hem, and does the reason explain the assertion? Perfectly, chromium moves an electron precisely to reach that stable half-filled D. Both true. Reason explains. Option A. Second one, the assertion, the force orbital fills before the 3d orbital. The reason, the 3d orbital is spherical in shape. The assertion is true by the n plus L rule. But the reason is false. The 3d orbital is a clover leaf, not a sphere. Only s orbitals are spherical. Assertion true, reason false. Option C. This is the chap that catches John, who accepts a true-sounding reason without checking it. Third one, the assertion, a 2p orbital has one radial node. The reason, the number of radial nodes equals n minus L minus 1. Check the reason first. It is true. That is the correct formula. Now the assertion, for 2pn is 2 and L is 1. So radial nodes equal 2 minus 1 minus 1, which is 0, not 1. The assertion is false. The reason is true. Option D. A quick match now. Say each node count aloud before I reveal it, using total nodes equal n minus 1. The 1, s orbital, n is 1, so n minus 1 is 0. 0 nodes, the smoothest orbital that is. The 2's orbital, n is 2, so n minus 1 is 1. 1 node. The 3p orbital, n is 3, so n minus 1 is 2. 2 nodes. And the 3d orbital, n is again 3, so n minus 1 is 2 again. 2 nodes. Notice that 3p and 3d share the same total because they share the same n. If all 4 came to you before the reveal, the formula is becoming yours. Here's a favorite new NEET format. I will read some statements. You silently count how many are correct. Statement 1. A p subshell has 3 orbitals, so the number of magnetic quantum values is 3. Hold your verdict. Statement 2. The 2s orbital has 0 radial nodes. Think n is 2, L is 0. So radial nodes equal 2 minus 0 minus 1. Statement 3. Copper's ground state configuration ends in 3d10, force 1. Recall the anomaly we just met. So, how many are correct? 2 statements, the first and the third. A p subshell truly has 3 orbitals and copper truly ends in 3d10, force 1. But the second one falls. The 2s orbital has 1 radial node, not 0, because 2 minus 0 minus 1 is 1. 2 correct. Statements 1 and 3. Now let me save you some marks. 2 traps that catch thousands of students every year. Myth 1. The number of nodes in an orbital equals n. It feels tidy, but it is wrong. David believed this for months and kept overcounting. The truth. The total number of nodes is n minus 1, never n. A 3s orbital has 2 nodes, not 3. Always subtract 1. Myth 2. A d subshell has 5 magnetic values simply because someone said so. The truth. It is true, but know the reason. The count is 2l plus 1, and for d, l is 2. So 2 times 2 plus 1 is 5. Use the same rule everywhere. S gives 1, P gives 3, D gives 5, F gives 7. Count with the formula, never by guessing. Time to test yourself, rapid fire. Here's the rule. I ask, you answer in your head before the reveal. No pen, no paper, just the formulas you built today. Question 1. How many total nodes are in the 3p orbital? Total nodes equal n minus 1, so 3 minus 1, 2 nodes. Question 2. How many of those are radial nodes? Radial equals n minus L minus 1, so 3 minus 1 minus 1, 1 radial node. Question 3. How many orbitals are there in a d subshell using 2l plus 1? L is 2, so 2 times 2 plus 1, 5 orbitals. Question 4. How many unpaired electrons does chromium have? 3d5, force 1, 5 plus 1, 6 unpaired electrons. And question 5. The classic. Which fills first, 4, C, or 3d? By the n plus L rule, force has the smaller sum, so force fills first. If you caught everyone, you have truly understood today's class. Let us gather the whole class in one slow breath. 4 quantum numbers, n, l, m, and s. together give an electron its full and unique address inside the atom. The s orbital is a sphere, the p a dumbbell, the d a cloverleaf, and the total number of nodes is always n-1. Each subshell holds 2l plus 1 orbitals, and each orbital holds exactly 2 electrons of opposite spin. Fill by Aufbau, Pauli and Hund, and let the n plus l rule set the order of energies. Half-filled and fully filled subshells are extra stable, which is why chromium is 3d5, force 1, and copper is 3d10, force 1. And next class, we step back to see the whole family. Classification of elements and periodicity. The periodic table and how properties repeat in beautiful trends. Do not miss it. And so, my friend, we have gone right inside the atom. It may have looked like just 4 numbers and a few strange shapes, but understand this. Everything about an element flows from where its electrons live. Its size, its reactivity, its very place in the periodic table, all of it is written in the configuration you learned to read today. Sarah, David, Lisa, and John all started exactly where you are right now, with this one class. Be patient with yourself. Tonight, once, slowly, write out chromium and copper by hand. One idea at a time, you will crack NEET. Of this I am certain. If this class brought you clarity, subscribe to the channel so the next one finds you. Until then, keep going. I will see you at the periodic table.